Hello everyone, in this video I'm going to show how you can do holdout method for linear probability models. So I'm making this video because if you check assignment 3 this week, case 2, the third question is asking to compare linear probability model with logistic regression. You can find holdout methods and logistic regression in the course webpage, but I didn't have how you can apply holdout method to a linear probability model. So what we are going to do is we are going to apply holdout method to linear probability model and then learn how to calculate the accuracy rate for validation dataset. If you read chapter 7, you realize that we have to partition the data to training and validation dataset. The training set is used to build the model and validation dataset is used to measure the performance of the model. The idea is simple here. The training dataset is used because we want to build our model, and validation dataset, which is an unseen, the model didn't use that dataset, will be used to measure the performance of the model that is built in the training dataset. That's why we do all performance measures in the validation dataset. Because you may think about that as an out of sample forecast. So in sample, which training dataset you build the model, out of sample, which is an unseen data, you test your model whether it performs when you apply to an unseen data. And at the end, we will calculate the accuracy rate for validation dataset, and you'll calculate an accuracy rate for logistic regression, and the more accurate, the better the model is. So on the screen, you see a dataset. This is a parole dataset. So let me briefly give an information about this dataset so you know what we are doing. More and more parole boards are using risk assessment tools when trying to determine an individual's likelihood of returning to crime. Most of these models are based on a range of character traits and biographical facts about an individual. Many studies have found that older people are less likely to re-offend than younger ones. In addition, once released on parole, women are not likely to reoffend. So here, a sociologist collects data on 20 individuals who were released on parole 2 years ago. And sociologist notes if the parole committed another crime over the last 2 years. So therefore, crime is equal to 1 if crime committed, 0 otherwise in the last 2 years. And the second column is the age of the parole at the time of release. And the third column is the parolee's sex. It's equal to 1 if the parolee is male and 0 otherwise. So what we are going to do is first we are going to build the model, and I'm going to use 15 data points for training dataset and 5 data points for validation. We have total 20 dataset, so 15 to 5 is the partition. So we are going to use the first 15 data points for training and the last 5 points for validation. In real life, you randomly assign a training dataset. For teaching purposes, I'm assigning the first 15 data points for training and the remaining 5 to validation. But in real life, you are going to randomly assign and you are going to randomly partition the data for training and validation. So first create a new variable called flag and then say this is going to be my training, and until 16 you have the training dataset, and the last 5th observations is your validation. 1, 2, 3, 4, 5. And let's first build our model. To build our model, you know that we need a target variable and the predictor variables. My target variable is crime, whether the person commits a crime or not, and my predictor variables are age and male. So I'm going to click data here and then data analysis. If you remember, linear probability model is just a regression, so I'm going to choose the regression here and then click OK. My input y range, which is our target variable, and I'm selecting the data until and including row 16, and for xput range I will do the same. And since the first row contains the labels, headers, I'm going to click labels. Let me have the output in the same worksheet, therefore I'm going to click F1 here and then click OK. Now you can see the model here. Our model is the coefficient estimates. So our model is here. We are going to predict y hat is equal to b0 plus b1 x1 plus b2 x2. So when you look at this y hat, we are predicting crime. So we are predicting crime here. And x1 is age. and x2 is the gender or male. And here B0 is our intercept, B1 is the slope coefficient for age, and B2 is the slope coefficient for male. So if we plug here, we are not going to predict y hat, but we are going to predict a probability of committing a crime. So if we plug here, let's say for B0, 1.61, I just rounded, plus instead of B1, negative, let's use this, negative 0.043 times x1, and then 0.37 times male. So this equation is going to predict our probability, which this probability is going to help us to determine the crime, predicted crime. So let's do that. Let's use the model here. This is my predicted probability. P is equal to, I'm getting intercept and then click on F4 to fix it, okay? When I drag down, I want to use the same intercept for all other predictions. And then I'm gonna choose slope coefficient for age and then fix it and then times age. Age is 25 for the first observation. Plus, and then male again, I'm going to fix it times the first observation is male, which I'm going to select male. And now this is my prediction. Okay, 0.88, 88%, this person is going to commit a crime. Okay, this is my prediction. And I will continue to do for all training data set, right? And I'm going to use this model for the validation data set too. So I will continue to drag down till here. So let's predict crime, okay? So this is going to be our crime or y hat. I'm going to write it y hat, but it's in fact y hat is our target variable. So we are going to predict crime with the model that we created. So our cutoff value is going to be 0.5. So that means the probability is greater than 50%, then the person is predicted to commit crime. So here we are going to use if function. If the probability is greater than 0.5, you can use greater than equal to, let's use greater than equal to 0.5, then the prediction is 1, otherwise 0. And then close the parentheses and enter. So you see the first observation is predicted to commit crime using our model. And now we drag down this. You see the prediction is 1, actual variable is 1. So we truly predict. For the third, fourth, fifth observation in actual data, the person didn't commit crime in the past 2 years and our model predicts the same. Okay? So you see our model predicts, but let's try to understand, are we actually doing a good job in the validation data set? So how we know that? If our prediction matches the true value, then it's accurate. So let's look at our validation data set. Starts from here. So highlight this part. Yeah, so let's check. Actual value is 1, prediction is 1. Yes, so this is accurate. But how we can do it if we have lots of data? We can again use the if function. If, open the parentheses, the prediction is equal to actual data, then return true. Otherwise, return false. You see, the first observation in the validation set turns to be true. So the actual and prediction matches. And we can drag down this and find out that we have 3 true values. So out of 5, 3 of them are correctly identified by our model. So what is the accuracy rate? Count the number of true values, right, which is 3, divided by count the number of all observations in the validation set. And now you see the accuracy rate is 60%. This is how you calculate the accuracy rate for linear probability model. You will have accuracy rate for the validation data set for your logistic model, and you compare them and choose the model that actually does better job in terms of accuracy rate. I hope this video is helpful. Thank you for watching.